We're now on section 9 of this course, which is concentration cell, polyoxidant, ampholyte, and dismutation. Okay, so first we're going to look at concentration cells. What do we mean by that? It means that we have the same electrode on both sides, okay, of a battery or of a galvanic cell. So in this example, I have the anode is copper and the cathode is also copper. Okay, when the cell concentrations are equal, there is no difference in energy between the half cells and no electrons flow. If I have the concentration here of copper 2 plus the same as on this side, then there is no flow of electrons anymore. It's possible to get a spontaneous reaction when the oxidation and the reduction reactions are the same, as long as the electrolyte concentrations are different. If you look at the reduction and oxidation reaction, so this part is the oxidation, this part is the reduction. They're the same reaction, only written in the oxidation way and written in the reduction way. For electrons to flow, the concentration of copper on this side must be different than the copper, the ion. Copper 2 plus and the copper 2 plus must be different. So this is called a concentration cell because it only varies in the concentration of the copper 2 plus ion on both sides, the oxidation half and the reduction half. And usually the concentrations are in the brackets if we have it written in the cell diagram way. Now, for the next piece that we're going to do is a nickel example of a concentration cell. So here we have nickel at the anode, nickel at the cathode, and the nickel 2 plus concentration on the anode side is 1 times 10 to the minus 3. And the nickel 2 plus on the cathode reduction half reaction side is 1. Okay. When this has a certain voltage, okay, and EMF, this EMF becomes 0 when the concentration of nickel is the same, okay? And it's very logical for you. When do we say that the concentration of nickel is the same? Well, if we're saying that nickel 2 plus, look at the bottom, and nickel 2 plus on the anode and the cathode are equal, that's when E of the cell equals 0. Then it's almost like we're taking the average of the two nickel concentrations. So 1 plus the 0.001 divided by 2. So we can already figure out what is the nickel 2 plus when the E of the cell reaches equilibrium, and it's simply going to equal 0.5. Now, what is the E of the cell at the beginning of the reaction? Okay, let's see. What is it at the beginning of the reaction? Well, we have here the cathode and the anode, and each of them has its reduction potential first. And we can have a corrected reduction potential for E at the anode and for E at the cathode. Okay, so are you guys with me at this point? Yalla, you do it with me, please. هذا منكم. Guys. I want the reduction potential. يلا مين معي؟ you guys hear me? ما في speaker نشوف. There is a mic. Do you guys hear me? Hello?
Yes, doctor.
Okay. Yalla, do this with me, please. I want reduction potential, E at the anode and E at the cathode. Now notice something. In both cases, even though I have the equation oxidation, I still use always the reduction potential, okay? For each corrected. So E at, let's do E at the cathode because it's already in the form of reduction. E of the nickel couple, nickel 2 plus ox على red equals, يلا شي معي. E للنيكل، أنا بس هيك بكتبها لأنه E ناد للنيكل، يلا.
Minus 0.0592 over 2.
Okay. Do you think it's better to do a minus or a plus if I'm doing in this case?
We can put a plus لأنه ما في عنا غير concentration Ni 2 plus.
Exactly. So plus 0.0592 على 2 electron transferred log
concentration
of
Ni
the
2 plus.
ox على red. Nickel 2 plus الox على red. Okay. So, and so now here, what is this number? In the cathode side, it's 1, correct? 1 molar. By the way, for the reduction reaction of at the anode side, does it differ in this than this equation? E of the nickel. Yalla, help me out. Is it any different?
No, the equation is the same.
Exactly. So plus 0.0592 على 2 log of the nickel 2 plus concentration at the anode side, which is 0.001. And so when we solve this, the equation is the same, but when we substitute, the concentration differs only. So this becomes minus 0.368. And clearly this is simply equal للE نود. لاحظين لأن هيدا log of 1, which is 0. So this term becomes 0. So this part here at the cathode simply equals the E node of the nickel. It's not always the case, but anyhow, yes? Because it doesn't need correction because it's already at 1 molar. And we already said that at 1 molar, يعني we are already at standard. But in case على الامتحان you're not necessarily thinking, and we did it, it comes out to be the E naught. Okay, so we found the reduction potential at the cathode and anode. To get the E of the cell, E of the cell is
E cathode minus E anode.
E cathode minus E anode. So minus 0.28 minus 0.368. Yes? Which equals, you'll find the number, whatever it is. Now, what about the E node? The E node of the cell. The E node of the cell equals كمان E cathode minus E anode at standard. But at standard, the cathode and the anode is the same. Okay, at standard conditions because they're the same cell. So E naught of the cell is equal to 0 always. For concentration cells, E naught is equal to 0. Okay, let's now do it another way. E cell equals E cathode minus E anode, and substitute only in terms of the equation and not in terms of numbers. Minus 0.0592 divided by 2 log 1 على nickel cathode minus 0.592 log 1 على nickel of the anode. And here they used the minus sign, so the nickel went to the bottom. It's fine. Okay, then they put the minus in and the nickel came up to the top. Okay, that's better. And here they put the minus in, the nickel came up to the top. So this is the two equations. Now if I factor out the 0.0592 divided by 2 with a negative sign, log, you get log nickel, because if it's with a negative, this nickel 2 plus becomes positive nickel 2 plus of the anode, and there becomes a negative sign in front of here. And if I bring it to the inside, it becomes 1 over nickel. So it becomes nickel 2 plus of the cathode. This equation can be used all the time. By the way, why, what about the E nodes for each of them? Well, actually, this part already should have an E node of nickel at the beginning of it, and this part should have an E node nickel at the beginning of it, but they're both equal. That's why they cancel each other out, and that's why you only have the second part of the Nernst equation in the overall E of the cell, because E node of the cell is 0 for concentration cells. Okay, so E of the cell is minus 0.0592 divided by 2 log nickel at the anode divided by the nickel at the cathode. Usually, it's the lower divided by the higher concentration. And this equation can be, solved right away instead of, doing all these calculations. Automatically, if you have only one metal ion in your equation, you take the E of the cell will be 0.0592 divided by the number of electrons transferred log the lower concentration divided by the higher concentration. Okay. And it's very logical because usually the higher will go to the lower and the overall reaction. And the higher concentration will usually have the higher E, and therefore it will be the cathode, and the other one will be the lower E, it will be the anode. And that's it. And that the overall concentration of the manganese 2 plus at equilibrium, or N plus, at equilibrium is the summation N plus the other manganese of high, low, divided by 2. That's the overall manganese at equilibrium. A useful general equation to use whenever you have concentration cells. Okay, the next section. Any questions first on concentration cell? Any questions? Okay, the chemical species that can both gain and lose one or more electrolyte is called an amphoteric species. This is exactly the same as the ampholyte in acid-base reactions. It can be either it can gain a proton or lose a proton. Here it's a species that can gain or it can lose one or more electrons. This species is thus both an oxidant in a couple and a reductant in another couple. So this element our species can have several oxidation states successively participate in many separate reactions of electron exchange. Examples of such species are the iron, the tin, the chromium, and the copper. And we're going to see how some of them act as both oxidizing agents and reducing agents. A disproportionation, also called a dismutation, is a reaction, redox reaction, in which one compound of the intermediate oxidation state, an ampholyte, converts to two compounds, one of higher and one of lower oxidation states. Let's discuss exactly what we've been talking about. Let's look at this copper plus, for example. Copper plus can go to copper 0 with a E node of 0.52. As well, copper 2 plus can go to copper with an E node of 0.34. And copper 2 plus can go to copper plus with an E node of 0.16. So we can see copper having many oxidation states. It could be copper with a 0, copper plus, or copper 2 plus. As well, I could see this. Look at this guy, copper plus. He is an oxidant here. Yet, in this equation, he's on the reductant side. Clear? And so this copper plus is an ampholyte. It can act as an oxidizing agent in some equations, depending on which equation he's in, or he can act as a reducing agent in other equations. So he's on both sides. Now, what happens if I put copper plus in a container just by himself? It turns out that just by himself, because one of the coppers can act as a reduction and the other can act as a oxidizing agent and the other as a reductant, they can actually react spontaneously with each other. And so you end up getting an equation. Copper plus another copper plus becomes copper 2 plus and copper. And this type of equation is called a disproportionation or dismutation, where one species of copper with a certain oxidation number, in this case +1, becomes another, the same copper, but one with a higher oxidation number, 0, and one with a lower oxidation number, 2 plus. Okay. Are we clear?
Yes, doctor.
So we're calling this copper plus or copper 1 is an ampholyte. It can be an oxidant or a reductant. Is it stable in water? If you have a spontaneous reaction between this copper and himself, then we call he's not stable. And automatically what happens is all of the copper plus becomes copper 2 plus and copper 0. And actually we cannot buy copper plus. No, we can't actually get copper plus on its own. The consequence is that this copper cannot exist in aqueous solution, and it is in fact either in the form of copper plus or copper, the couple that determines the redox reaction of copper in water. So whenever I have copper in water, it acts as if it's copper plus, 2 plus or copper 0. The opposite of disproportionation, okay? Let's look at an example of where I do not have disproportionation, yet I have an amphoteric species. Vanadium exists in multiple oxidation states. It could be vanadium 2, 3, 4, or 5. Okay, so let's look at this vanadium. Vanadium 5 goes to vanadium 4, has an E node of 1. Vanadium 4 goes to vanadium 3, has an E node of 0.36. And vanadium 3 goes to vanadium 2, has an E node of minus 0.35. Okay, so in green, I could see vanadium 3. Okay. On the oxidation and on the reduction half. I could see vanadium 4 on the reduction and on the oxidation half. Okay. So they are vanadium 5 and vanadium 5 and vanadium 2 is a polyreductant. Is a polyoxidant, and vanadium 2 is a polyreductant. What do we mean by that? Polyoxidant. And if vanadium 5, look, he can react with vanadium 3, he can react with vanadium 2. He has that choice. As well as a reductant, vanadium 2 can react with vanadium 4, okay, or with vanadium 5. So they can react with multiple vanadiums. Vanadium 3 and 4, which is in green and in blue here, okay, they are oxidants, they are amphoteric or ampholites, but they are stable. Why are they stable? Why is vanadium 4 considered stable? Okay. Well, first, before answering that question, vanadium 5 can react, we said, with vanadium 3. There we go. We get vanadium 4. But what else do we get? Only vanadium 4. We only obtain one product, and we look at it as if it's 2, but it's only a single product. And vanadium 5 here. Okay. So vanadium 5 with vanadium 2. No, 4 with 2. Let's look at 4 with 2. We get vanadium 3. Only a single product. Okay. That there is no particular name for this. Okay, a process. But sometimes we can mix an oxidant and a reductant with same different oxidation number, and we get the same product. Okay. Now let's see why vanadium 3 and 5 are actually stable while this copper 2 plus was not, or copper plus was not. If I look at vanadium 3 and I put him in a solution, will he react with himself? That's the question. That's the idea of stability. Will he react with himself? Well, let's take the vanadium 3 and vanadium 3. What happens? It's in the anti-gamma direction. And therefore, the reaction is not spontaneous. And therefore, the vanadium 3 is considered stable. Likewise, vanadium 4 and vanadium 4, if they put them in a solution, they won't react with each other. They're in the anti-gamma direction. And so there is no disproportionation. They are ampholites, but they can act as oxidant or reductants, but they are stable under standard conditions. Are we clear about this difference? between stable and unstable amphilites. This copper, remember, is not stable because copper with another copper, it's in the gamma direction, and that means it'll be spontaneous, and therefore copper plus is an amphilite that is not stable. That's it for this part.